Hi everyone, we're now going to learn about chemical measurement in our chemistry lesson. This is now the quantitative part of chemistry. I still encourage you to take down notes so that you would have some documentation on your binder and you can go back to that anytime you want. When we talk about measurement, there's always a possibility that there is uncertainty that will take place. And what does uncertainty mean in measurement? It means to say that there is a chance that you might be able to get errors in your readings. Now, for you to be able to lessen that error, you have to understand that you should know how to express the number of figures when you report your measurement. This is very critical, most especially in our chemistry lab work, for it gives us the accuracy or the precision of the measurement. Later in our lesson, you will be able to learn the topic called significant figures and apply these rules so that you know how to count or determine the number of figures. But before that, I would like to describe to you the two words that are often used when we speak about measurement and this is most especially important in science. These are the words precision and accuracy. If you see here at the bottom of your slide, I wrote the definition of the two words. So accuracy comes from the root word accurate, which means to say when you have measurements, the measurements are close to the correct value. Correct value is also called the target value. In some chemistry books, it's also called the accepted value. While precision comes from the word precise, meaning what you have or what measurements you got may not have reached the correct value, but they seem to be very close to each other. So it means to say your measurements are precise. To give us a little more idea in how to understand this, I will be using numbers so that you understand what precision and accuracy mean. All right, let's say that you are doing an experiment and you're given a target value or accepted value. Let's say you're reading a volume. So the accepted value is 35 milliliters. Okay. Now you got one, two, three trials. So this is your trials. Let's say on your first trial you got 19.5 ml. Let's say this is one student who's doing this work, okay? And then her second trial, she got around 22.5 ml. And then next is 30.1 ml. This is for one student. Another student gave another trials, and this is what she got. All right. Another student shared her work, and this is what she got. All right. Now, based on these three data that we can see, can we describe now, which is good precision and good accuracy, or poor precision or poor accuracy? So for this data here, you can see that the trials are way off from the true value, which is 35 ml of volume. So I can say here that in terms of accuracy, it is poor accuracy. And in terms of precision, I can see now that the value are not that very close to one another. So I would say this is also poor, sorry, it's pure poor precision. In the next data, you will see here that again, the student have not reached the target value or was not very close to the target value. But if you look at her trials, you will see that they seem to be very close to one another. So like this one, it's just a difference of zero point 0.5 from the first trial. The second trial is also like 1.5 off, but just the same, they are way close to one another. So in terms of accuracy, we can say that it's poor accuracy, but in terms of precision, I will say it is good precision. Again, based on what we have learned on the previous slide, we say that precise means close to each other. Last but not the least, let's look at the last data of the student, and it says here 35, 34.5, and 34 ml. Now, if you look at the target value, this student have really reached the target value or have hit the target value. So, as we describe this in terms of accuracy, we can say this is good accuracy. And in terms of precision, if you see they're very close also to one another and very close to the correct value or target value, so we can say that this is also good precision. I hope this little example I have given you in numerical value have given you a clear understanding between accuracy versus precision. On the next slide, I'm going to show you another analogy which can somehow give you more understanding of these words if you still don't get this, and what that is the one that I will be sharing to you. All right. When we talk about precision and accuracy, it is nice that we come up with some analogy here, and this is what we call a dartboard analogy. I'm sure some of you have experienced um, playing a dartboard game. All right. Now, what is the main goal when you play a dartboard game? Is technically you want to hit the bull's eye. So we will assume now that the bull's eye, sorry, the bull's eye is your target value. Okay. So let's look at this dartboard A. This would be dartboard B and dartboard C. So on the dartboard A, you will see that all the darts landed on the bull's eye. And all the darts really landed. Nothing was spread out on the other side of the dartboard. So we can say that's good accuracy and good precision. For dartboard B, you will see here that nothing landed on the bull's eye, but if you observe, all the darts landed on one area. So we can say poor accuracy, but good precision. And on the last dartboard, you will see none of the darts landed on the bull's eye. And also, if you observe, the darts landed in different areas of the dartboard, so they are widely scattered. So, in terms of accuracy, that's poor, and precision is also poor. I hope you are now able to get the difference between precision versus accuracy. Now we're going to learn the concept of significant figures, and I want you to take down notes on this and make sure you copy the rules in your notebook. As we speak about uncertainty in measurement, it is very critical, as I said in my first slide, that you need to report your numbers in correct number of figures. And this depends on what kind of measuring device you are technically using. So there is such thing that you could read it in tenths, you can read it in hundreds, or you can read it in thousands. When you do that, then you are giving a precise reading of your measurement. So if you look at this first bullet here in bolded font, I say the definition of significant figures. So keep in mind, this is how you report the number of digits that you report in a measurement. Now, when you signify a figure, you need to count them. Okay? So if you see here in the second bullet, it says here, figures known with certainty plus one extra figure are called significant figure. Let me just give you this part here and make it a little bit more clearer. So when you say certainty plus one extra figure means to say, for example, you have a reading of a volume of 21.5 ml. Okay, the certainty part here is actually 21. So you are certain that you are reading that volume of liquid in a 21 ml mark. Now the one extra figure, which is the zero point 0.5, is actually what we call your estimation. Now, is it wrong? No. But will there be an uncertainty on that? Yes. So, but that's okay. So, but that zero point 0.5 is still considered a significant figure in your reading. So, for us to understand the number of significant figures here, we will now have to learn the different rules that we need to follow. So, here we can say 21.5. How many significant figures are present? It is 1, 2, 3. So, there are 3 significant figures in this given measurement. As we get into the rules and you get the principles behind it, I will also teach you how to calculate, okay, using significant figures. So we will do the multiplication and division together and addition and subtraction together. But we will do that in a little latter part of our discussion. So let's begin. Be ready with your notes because I still want you to copy the rules on your lecture. All right. Here are the rules of significant figures. And I want you to memorize this and really put this in your head so that you know how to identify significant figures. Let's start with the first rule. Number 1. It says non-zero numbers are always significant. So when you say significant, it means to say you need to count them. So non-zero. What does non-zero mean is that anything that is not zero are significant. So if I have 25 ml and I have 342 cm, if I ask you now, how many significant figures do you see in 25 ml? That is 2 significant figures. How many do you see in the second example I gave? 3 significant figures. So what I'm doing is I'm just counting the numbers that I see. Okay? They are all non-zeros, so they are always significant. Second rule. Zeros between non-zero numbers are always significant. What does this mean? So for example, I have 201 centimeters. All right. If you observe, the zero is actually in between non-zero numbers. Non-zero numbers. So they are in between. Okay? So when the zeros are in between non-zero numbers, then we need to count them and they will be considered significant. So 201 centimeters will give us three significant figures. 5,004 milliliters. How many significant figures? It will be four significant figures. Third rule. Zeros before the first non-zero digit are not significant. Okay, so let's have an example here. It says 0.0003 has one significant figure, meaning this is the non-zero digit. Okay, sorry, the non-zero digit. So these zeros over here are not counted to be significant. We do not delete them, but we just do not count it as a significant figure. So therefore, how many significant figure or digit can you see in this measurement? It's only one, and that's your 3. And we have another example over here. So if I have point 0, I'm sorry, okay, let me see the point there very clearly. All right, I have a 0.00813. How many significant figures are in here? Is only 1, 2, 3. 3 significant figures. So these over here, okay, are not significant. That's rule number 3. Rule number 4. Zeros at the end of the number after a decimal are significant. So let's have an example. All right. Zeros at the end of the number after a decimal point are significant. So do you see the zeros here at the end of the measurement? It is after a number and it's written after the decimal point. So therefore, how many significant figures I can read on 5.850 centimeters would be 1, 2, 3, 4. 4 significant figures. In this measurement, again, we see the zeros at the end, and it is after a number, and it's after a decimal point. So that would be 1, 2, 3. 3 significant figures. Last rule, the fifth one. Zeros at the end of a number before a decimal place are ambiguous, meaning it depends on how the number has been written. Okay, so I'm going to give you an example here. Now, let's use this one that has 10,300 grams. Okay, if you see here, the zero here is not being written after a decimal point, but it's written after a number. So at this point, the zeros here will not be counted. You don't delete it again, you just do not count it to be significant. So my answer would be 1, 2, 3, 4, 5. I'm sorry. I'm sorry, I stand corrected. That should be not. That would be 3 significant figures. Now, if I have 10,000, comma, 300, and what I do here is that I put a decimal point, okay, that is very, very obvious, in grams. How many significant figures are now present? With the presence of this of the digit of the decimal point, the zeros here become significant. So we will now count 1, 2, 3, 4, 5. In some books, they even use another character instead of a decimal there. They use it. They use a bar on top of the zeros. So when you see that, it just tells you that they want you to include the zeros to be significant digits. So that would be again 5 significant figures. I will stop on the slide so that you will be able to absorb everything that you have learned from me so far. You will be given a worksheet to work on this. If you have other questions, I am going around so that I can assist you with your concern. Again, you're very welcome to go back to my video and look again all the slides that we have learned so that you can understand the lesson. Thank you.